Um, so here we go with chapter 1. We're going to be doing circuits and DC instruments. And so far we've covered capacitors. That's what they look like. A battery voltage supply, DC voltage supply. That's what that looks like. And then we have our resistors, R. And then we have voltage AC, so alternating current with the little squiggly tilde in the middle. So we're going to be talking about right now resistors, so the third one. We're going to be talking about those in series and parallel. So here's a bunch of resistors in series. And we're going to talk about why that equation, the equivalent to those four resistors, we're going to talk about why that equation is true. Let me show that to you. And then we're going to talk about this one for parallel and the equation that goes along with that is the R equivalent for parallel and how that works. So if you notice, these things are very similar to capacitors, and they're opposite. So we're gonna find out why. Here we go. So I've got a little diagram there, and I know you can't see it yet, but we're gonna scroll up here in a second. So here's our new diagram. We've got a battery supply, we've got a R1, R2, and R3 going in series, and each of those resistors has a voltage drop across them. So the voltage drop is V1 for R1, V2 for R2, and V3 for R3. And the current is going around the circle has to be the same current all the way around, right? Because, conservation of energy and charge and all that stuff. So there's no way the current can be different. So if we look at the current being the same for each one, V1 then is I times R1, V2 is I times R2, V3 is I times R3. And if we factor out the I, then we have V equals I, and the equivalent of the resistivity, that's REQS right there in series, that equals I times R1 plus R2 plus R3. And so those two things are equal, and that therefore we have the series circuit equation for REQ. Now let's look at parallel. Okay, so here we have our voltage, DC voltage supply. It's got current going in and coming out of these parallel resistors. And along with R1, we've got I1, and then R2 has I2, R3 has I3, and there's a voltage at the top and a voltage at the bottom, VA and VB, top and bottom. The total of I total going in and out has to be equal to I1 plus I2 plus I3, right? Because we are not making up additional current, so that can't happen. So we know that at least, and we also know that the voltage across is the same, VA to VB. That voltage drop is the same as the voltage that is supplied by the battery or our DC voltage supply. So V1 has to equal V2, has to equal V3. And that's great. So V1 equals I1 R1, which is just a statement of Ohm's law. And therefore we can then solve for I1 and get the current that's going through R1 by taking V1, which is V, and dividing it out by R1. So we're going to use that I1 plus I2 plus I3 equation And we've got I equals V over R1, V plus V over R2 plus V over R3. That goes to I and equals, and then we just factor out the V. And we have our 1 over R1, 1 over R2, and 1 over R3, and that is our equivalent resistance in parallel. Okay, hopefully there are no questions on that, but let's do an example. We've got resistors in parallel and series combined. Now this example isn't exactly finding out what the resistivities, it's finding out what the equivalent resistivities are in a hard situation. Okay, so I'm making this thing really hard. So what is the total REQ is the question, but we have to cut this thing up and break it up into little pieces and whatnot. So here we go. We've got R3, R4, and R5 that are going to be 1 REQ, R3, R sub 3, 4, 5, or R3 to 5, whatever I wrote, I can't remember. And then we've got the other one, R6 and R7. Those are equivalent, or we're going to have equivalences there. Then we're going to do an equivalent of R3, 4, and 5, R6 and 7. We're going to do that equivalent because they're in series. And then we're going to include R2 with that, and then we're going to include R1, and then that R1 will give us our total REQ. Okay? So let's do R6 and 7 first. And we're doing R6, 7 the hard way. Just so that you guys can see it actually happening in real time. And I know you can't see right now, but I'm going to raise this up here in a second. We'll talk about it. I'm pretty sure I do anyway. There we go. Okay. So I wrote down what all the resistances were. 6 is 8 ohms, 7 is 7 ohms. We want 1 over R67 because we're trying to find R67, and those two things are in parallel. Okay, so we do 1/8 over 1/7. We factored out our 1 over ohms units, and 1 over 8 is 0.125. 1 over 7 is 0.1429. Add those together, we've got 0.2679. 1 over R67 equals 0.2679 times our units of 1 over ohms. That goes, when you invert it, that goes to 3.73 ohms, okay? So we've inverted the equation. That's the first step after my arrow there. We've inverted it. So R67 is in the numerator, the ohms are in the numerator, but that throws the 0.2679 into the denominator. Then you invert that number, giving you your 3.73 ohms. That is the final invert right there. So now let's do 3, 4, 5. And 3 is 11, 4 is 10, 5 is 9. So we're going to come back down here. And when I first recorded this video, I did it very quickly because I'm going to do it for you right now. So we're doing 3, 4, 5. Look how it says 3.31 ohms right there. Here's what I did. Okay, we start with 3. So we've got 11 ohms. 1 over 11 ohms. 4, 10 ohms, 1 over 10 ohms. 5, 9 ohms, 1 over 9 ohms. Okay, so I've done 1 over each of those things. I'm adding them together, bing, bang, bong. And then I'm doing the inverse to get 3.31. And then, of course, there are other digits, but it doesn't round up, so 3.31, that's the ohms. That's how fast that should be, that even though it took us, R67 took us forever to figure out that it was 3.73 ohms, it should go very quickly on your calculator. So I know it's a pain, but you just kind of have to go with it. So let's do R3 and 7, 3 through 7. We don't have to do anything but add 373 to 331, and that gives us our 7.04 because they're in series, right? Those two equivalent things are in series. So R3 through 7, I underlined it there on the right, is 7.04 ohms. Okay, let's keep going. R2 through 7. So we're now including R2 with R3 through 7. That requires, because they're in parallel, that requires us to do our inversion thing. So did I not write it down? Well, I'm going to tell you what it is. Because we've got 2. So let me, R2 is 6, so 6 inverted. R3 through 7 is 7.04, 7.04 inverted. And we'll add those two together, and then we'll invert that. That is 3.24. 3.24 is R2 through 7, okay? 3.24. It looks like I'm not writing that down for some reason, or I didn't capture it, or I don't know what's going on. I'm having technical difficulties. Okay, so R1 is the only one that's left out, and if our number is 3.24 and R1 is 12 and they're in series, all I have to do is add 3.24 to 12. So I'm going to do that real quick, and I get 15.24. And so 15.24 should be the final resistance on that. And I'm not sure why that isn't written down before we move on to this next little bit. That's kind of crazy. Okay, so I keep bouncing back. All right. So now let's do current as well, because we want to, many questions will ask us what the current is running through each of the resistors. And so we want to know how to do that. So here we're going to draw out our battery. We've got our resistance. We've got a parallel set of resistances, R2 and R3. And we want to know what the goal here is to find out what I1 is, I2, and I3. Okay? So that's our goal. And the first thing we need to do is figure out what the total equivalent resistance is. Because V, Ohm's law, V equals I R EQ, right? So whatever that I is, that happens to equal I1 going through R1, you can see that on the diagram there. Whatever that I is, we want to know what it is, right? So we have to figure out what the total equivalent resistance is. So we have to figure out what I23 is first. and they're in parallel. So we're going to do 1 over 5, which is 0.2. We're going to do 1 over 20, which is 0.05. And we're going to add those together. So we get 0.25. And then when we invert, we're going to end up with R23 is equal to 4 ohms because 4 times a quarter is 1. Okay, everybody knows that. All right, so we've got our 4 ohms is our equivalent R23. All right. Now our total equivalent is going to be R23 plus R1. So R23 plus R1 is 4 plus 2 is 6. So I wrote R23 over there and cleared the screen a little bit. Now our REQ then is R1 plus R23, and that's 6 ohms. Okay, that's just what I said, and that's perfect. I didn't box it in, but that's okay. So now we're going to come back down to this V equals I REQ. Solve it for I equals V over REQ. Our V is 40 volts. Our REQ is 6 ohms. And that gives us 6.67 amps. So we'll put that off to the side as I1. And it's also our total I. And we want to know what VP is. So we've got a voltage drop across V1 over R1. So that's the voltage drop across R1 is V1. And I show those there. You can see that to the right of the circuit. And across R3 and R2, we have the voltage drop of VP for parallel voltage drop. And if you notice the boxed equation, of course, the total V would have to equal the voltage drop across 1 plus the voltage drop across the parallel resistors. Solving that for VP, we get VP equals V minus V1. So what we really need to do is figure out what V1 is, and V1 is I1 R1. So we do that. We multiply 2 times 6.67, we get 13.3. Then we subtract 40, from 40 we subtract 13.3 and get our 26.7. So now we've got our VP. Okay, not a very important person. It is or vice president of something. We don't care about them. We've got R2 and R3 with a certain voltage across them. That's going to allow us to use Ohm's law and get the current on each one of them. Okay, so that's where we're going now. And I had to scroll up to do it. And I'm zooming in on the parallel part. Okay, so R2 and R3. We've got VP going across them, and we want to know what each current is. So I2, of course, is equal to our VP divided by R2. So 26.7 divided by R2, which is 5 ohms, gives us 5.33 amps. I3, similar deal, 26.7 volts, 20 ohms gives us 1.34 amps. Now let's talk about this for a second. Because R3 is greater than R2, most of the current then is going to go through R2 instead of R1. I mean, instead of R3. So, in fact, just about 4 times as much goes through I2 as I3. As much current goes through R2 as R3. Okay. I think you guys get it. So I3 has to be less than I2 when R3 is greater than R2. Okay. So our answers make sense, and we can move on to something else. Let's see, what are we doing here? Oh, this one is the exact same thing, only I'm doing it really fast. But I did the last one pretty fast too. But this is the same thing. I'm doing it again, but with different numbers, 3, 4, and 5, and with a total voltage of 12 volts. I want to know what I1, I2, and I3 are. So the first thing I do is I find the equivalent voltage for the whole shooting match. We found that R23 is 2.22 ohms. Our equivalent then is 5.22 ohms because you're adding 3 to 2.22. Then our next step, what is I? The I total would be our V, which is 12 volts, divided by our R equivalent, which is 5.22. That's 2.3 amps going all the way around. The next thing we do is we need to find out what V1 is so we can find out what VP is, right? What is VP? V1 first is 6.9 volts. 12 minus 6.1 or 6.9 leaves us with 5.1 volts. That's our VP. And we take that and we use it to solve for I. I2 equals VP over R2. That's 5.1 over 4. That's 1.28 amps. I3 equals 5.1 over 5.0, which is 1.02 amps. And we've got all of the information that we need. And I just saved you guys a lot of time listening to my bull. I'm just kidding. I did save you some time on this one, though. So thank you for watching this. I hope that went well. And if you do have questions, of course, email me. I'm going to, we're going to stop this one right now and start up on the next one.